Okay, so this one is similar to the previous one, right? Right, you know, again, what happened? Well, here, what happens, well, we want we're choosing one card at random. We want the probability that the card is an ace or a king. So let A be the event the card is an ace. B is the event that the card is a king. So the probability of A, well, there's 4 aces in the deck, right? So that's 4 out of 52. The probability of B, that's also 4 out of 52 because there's 4 kings in the deck. Now, why are these events mutually exclusive? That is, why is the probability of A and B 0? A and B, the probability of that 0? Well, there's no cards that are both an ace and a king. So because of that, the probability of A and B is 0. You know, there's no card that's an ace and a king. So for OR, probability of A or B, right? We have the sum, probability of A, plus the probability of B, minus the probability of the intersection, which is 4 out of 52, plus 4 out of 52, minus 0 out of 52, which of course works out to be 8 out of 52. That's what we get here. So it's 8 out of 52. Any questions on this?
So if you were to say and, it would change the equation.
The probability that the card is an ace and a king?
Oh, never mind.
Wait, is that what you mean? Or?
Like I'm trying to make like for them to be like independent from each other, since OR makes them dependent of each other.
No, you just want to use the formula here.
Okay.
You would have to get each of these. You know, so the probability of A, well, again, there's 4 aces in the deck, right? So it would be 4 out of 52. For B, well, there's 4 kings in the deck, so the probability there would be 4 out of 52. And the probability of A and B, can they both occur at the same time? That is, can you draw a card that is both an ace and a king? Well, no, because there's no such card in the deck.
Okay, thank you.
Okay, you're welcome. Good question. So that's why this is 0. Okay, awesome question. Any other questions? Okay, well, the way we've done some problems already is we would list all the outcomes, right? You know, for like flipping the coin and rolling a die, we were able to list all the outcomes. There were only 12 in there. But not every experiment is going to be like that. You know, you're not going to be able to list all the outcomes in an event or the sample space. I mean, theoretically you could, but it's not efficient to do that. I mean, for instance, if you were to try the experiment of rolling a 6-sided die twice, you know, and you record the number on each roll, the sample space would have 36 outcomes. I mean, it's not terrible, but I don't want to list all those outcomes. Not to mention, if you did the experiment, instead of rolling a die twice, you rolled it 3 times. So if you did it with 3 die, then the sample space would have 216 outcomes. So in other words, with 3 die, you roll, 3 die. In other words, wait, let me fix that. With rolling the die 3 times, that's better. Okay. So so if you were to roll the die 3 times instead of just twice, there would be 216 outcomes there. You know, that's a lot, right? So we don't want to list all the outcomes, so we need a better way to count the number of outcomes. We need to be able to list them efficiently. Now, there are nice ways to list them. One way is using a tree diagram, but I want to demonstrate that. Now, to demonstrate this, what I'm going to do is I'm going to use an example from the textbook, and the example they give is, suppose you're at a restaurant and you can get an appetizer and then a meal. You're able to order that. For the appetizer, you have 3 choices. You can get soup, you can get salad, or breadsticks. For the meal, you have 5 choices. You can get a hamburger, a sandwich, hope I'm saying this right, quiche, fajita, or pizza. Those are the possibilities. But remember, suppose you can only choose 1 item from each category. In other words, you can only choose 1 appetizer and 1 meal. Well, how many different options do we have then? How many different choices can we make? I mean, you could theoretically list them all, but we want to do that efficiently. And one way to do that is using a tree. The idea is this: you have a common starting point here on top. So maybe it's an upside down tree, so to say. And from that top, okay, you can draw a branch for each choice from one of the categories. So for instance, from the meal, you could draw a branch for hamburger, a branch for sandwich, a branch for fajita, for quiche, and pizza. Right? So this handles the category of meals. We have 5 branches. Then from each of these, you would draw a branch for each appetizer. In other words, you would draw a branch for each choice from the next category. So here, this was all the choices from one category, right? You have a branch for each, as you can see. And then from each of these choices, you would list the choices through branches for the other category, in this case, appetizers, right? So if you think about it, if you get hamburger, that's one choice. And with hamburger, you can get breadsticks, soup, or salad. Bread, breadsticks. I ran out of room, so I just wrote it as bread. From the sandwich, same thing. You can write bread, you can get bread, soup, or salad. Same thing for these. And if you were to do this for each meal item, the tree would look like this. Again, I guess really it's an upside down tree because the branches are at the bottom. Normally with the tree, the branches are higher up. But this is what we have here. And now you can actually list all the items. Essentially what you do is at the starting point on top, what you do is you come down to the edge of a branch. See? You basically start from the very top and you work your way down. So for instance, one outcome would be hamburger, then bread, breadsticks. That would be one outcome. Then you can get hamburger or soup. That would be another one. Hamburger, then salad. Or another one would be sandwich, then breadsticks. Bread, breadsticks. Again, I ran out of room. That's why I wrote bread. Sandwich, then soup. That's another option. And you keep on going. And you would keep on going. And that's an efficient way to list, whoa, we're out of time, to list all the outcomes. I'm sorry, I went a little over. Let me stop.